Okay, folks, it's time for our next online lecture. Today, we're going to discuss inductance. Inductance. Okay, so let's just remind ourselves what we did last time. We were talking about Faraday's law, and so inductance is very closely related to Faraday's law. And let's just remind ourselves what that is. We derive this, we see that the curl of an electric field comes about from a changing magnetic field. And then the integral form of this then leads to this familiar relationship that the integral of the electric field around some loop is equal to the time rate of change of the magnetic flux through that loop. And this is also, of course, equal to the EMF, the electromotive force in a loop. Negative d phi b dt for this geometry where we have some loop. And we are talking about the electric field in the loop and the magnetic flux through the loop. Okay, so and so when we talk about inductance, then for inductance, what the question that we want to address is this one. Let's consider this scenario where we have one loop. I'll call that loop 1, and it has some current flowing through it. We'll call that current 1. And then we ask ourselves, what happens to a nearby loop? So now we have some other loop. Here, I'll call that loop 2. So what happens in loop 2 due to loop 1? That's the question. So what happens here due to this loop 1? And so to answer that question, what we do is so let's make that question more quantitative. We'll say how does current in loop 1 cause flux in loop 2? We'll just call that phi 2. That's the flux in loop 2. That's the question. So let's try to answer that question. So what we can do is we can just calculate the flux in loop 2, which is equal to, if this is some area, if loop 2 has some area called A2, and loop 1 also has some area A1, then the flux in loop 2 is simply going to be the integral over the area of loop 2 of the magnetic field that comes from loop 1, integrated over the area of loop 2. So that's the idea. And so let's calculate that then. Then let's calculate that. And to calculate that, we have to figure out what this B field is. And so let's do that. So if I have current, so we know from Biot-Savart's law that if I have some current going through this loop 1, then I can think of it as we can think of there being little lengths of that current, dl. And then we know that if we think of each little part of the loop is sitting at the source position, r prime, then we know then that creates a magnetic field at this field point. And so the question is, what's the magnetic field here in a membrane that spans loop 2? And so this will be the field point r. And so to get that magnetic field, we need to have this vector, which you guys have seen before. That's our cursive vector, r, is equal to r minus r prime, the cursive r. And so we then see then that the magnetic field at loop 1 at the field point R due to the magnetic field from loop 1 at the point R in loop 2 is going to be equal to mu naught over 4 pi, the Biot-Savart law, which will be the integral over loop 1 times I dl of loop 1. So that's this little dl1 right there. We have to cross the cursive vector r and then divide by r squared, the familiar Biot-Savart law. Biot-Savart. And so now what we can do is plug this in to our expression for the flux in loop 2. So then we see that phi 2 is equal to, let's just plug it in, and we're going to have, we'll just plug it in there, but we'll pull the current out front, and so I can write it like this, that phi 2 is equal to, I'll write it like this, I1, and then we'll just write this big hairy integral, which is going to be the mu naught over 4 pi times the integral over the area of loop 2, but now I have the Biot-Savart integral inside, which is the integral over loop 1 times dl1 cross cursive r over cursive r squared. But then I have to dot that into dA2 because I'm integrating it over the area of loop 2. But the thing to notice is that this is just a geometrical factor. And so this geometrical factor we'll call, it has a name, geometrical factor, and we call it inductance. Inductance. In this case, it's the inductance which is connecting loop 2 to loop 1. And so I'll write this as I1 times M2 1. And so the idea then is that flux in loop 2 is created by current in loop 1, and that they're linear, and the linear relationship is here, the inductance between loop 1 and loop 2 inductance. So that's the concept of inductance. And so this we can call this the we can think of this as the mutual inductance between the two objects, mutual inductance. And something that I want to point out to you, and you know that I like to do this, is to remind you of the electrostatic analog. And this should be reminiscent, the electrostatic analog, because everything in magnetism has an electrostatic analog, and the electrostatic analog is, of course, capacitance. Because you guys remember that we could take objects, I could take an electrode, 1, for example, and put him at some voltage, and then I could have another electrode, electrode 2. And so then we can see that there's then going to be there's then going to be some charge between the two. I'll call this plus Q, and I'll call this minus Q, and there'll be some charge between the two electrodes, and we see that there's going to be a relationship, the voltage between the two electrodes times, let's write it like this, voltage is equal to 1 over C times Q here, and so we see this reminds us it's the same as this idea of the phi in one loop is equal to the magnetic the inductance times the current in another loop. So I just want you to sort of see that we have the same kind of relationship. Instead of talking now about for capacitance we talked about voltage and charge, but for inductance we're going to talk about flux and current. So the flux is taking a similar role as the voltage here, and the charge is taking a similar role as the current. So I just want you to sort of see that analogy. So when we talk about inductance in your mind, you should just think of it's very similar to the concept of capacitance. Okay, but here's a question. A question that we should ask is, if I have phi 2, if I have two loops, here, let me draw the two loops. This is loop 1, and this is loop 2, and here I have I1, and suppose here I have some I2, then we know that we can write phi 2, the flux in loop 2, is equal to M21 I1. We just derived that. The flux in loop 2 is equal to the mutual inductance times the current in loop 1. But what about the reverse? How about this? Can I say that, what about the flux in loop 1? I should be able to similarly say that it's equal to the inductance M12 times the current in loop 2. And so, but then we can ask the question, what is the relationship between M21 and M12? Are these the same or are they different? Now, if we look at this formula that we just derived up here, I'll circle it. There it is. Then we see it's not totally obvious, because here we're integrating over loop 1 and area 2, and so it's not completely obvious what happens when we start interchanging these subscripts. But what we can do is let's take a look at it from a different perspective. So let's calculate the inductance a different way to see if we can understand better the relationship of this mutual inductance when we start flipping the order. And so what we can do is let's calculate inductance a different way. So we'll calculate the flux through loop 2 as we did before, but we're going to go about it in a slightly different way. We'll start the same as we did before. We'll have to calculate we'll have to integrate over the area 2, and we'll take the magnetic field from loop 1, and we're going to integrate that over the area of loop 2. But now what we're going to do is we're going to do it a different way, because now we're going to say, let's assume that the magnetic field from loop 1 is equal to the curl of the vector potential from loop 1, where A, of course, is I'll write that down, this is the vector potential. And so now we're gonna plug that in, and so now we can see that the flux in, sorry, I'm having a little problem with the magnification. So now we can see that the flux in loop 2 is equal to the integral over loop 2, the area of loop 2, but now the magnetic field from loop 1 is going to be del cross the vector potential from loop 1 dot dA2. And so, but this is very cute because this should look very familiar, because now we can play a little game, because this, we notice, of course, we can use Stokes Theorem. Because whenever we have an integral of a curl over an area, we know that we can turn it into a line integral. So this then is equal to the integral over, now it's the integral over loop 2. And so what we have is the integral of the vector potential from loop 1 dotted dl2, integrated over loop 2 from Stokes Theorem. And so now let's use the definition of the vector potential, because now we know the vector potential. If I have loop 1 and loop 2, then I know that if I have some I1 here and I have some DL here, then I know that I can calculate the vector potential at this point R. If this is, of course, my cursive R, that same geometrical construction, then what we have is that the vector potential due to loop 1 at the field point R, which is pointing to loop 2, I can write that using this formula that we've derived in the past. Mu naught over 4 pi times the current in loop 1 times the integral over loop 1 times dl of loop 1 over cursive over the distance r. And so that's the vector potential formula that we derived in the past. And so what we can do then is plug this here, and then we get a nice relationship for the flux in loop 2 due to the current in loop 1, because now we can write the flux in loop 2 is equal to the integral of loop 2 times this. So we're just plugging A1 into this formula, and so we get we can see that we can pull the I1 out, and so we're going to have well, we can write it like this. It's going to be we won't pull it out yet. It's mu naught I1 over 4 pi times the integral over loop 1 dl1 over cursive r. So that's A1, and then of course that gets dotted into a little differential line part segment of loop 2. And so now we can see that this is equal to, now we'll pull the current out, and we see that's equal to I1 times this expression, mu naught over 4 pi integral over loop 2 times the integral over loop 1 times dl1 dot dl2 over r. And as you can see, this then is the mutual inductance M21. But now so this is another expression, a new expression for the mutual inductance, a different expression. And what's nice about this expression is that we can immediately see that if it's the same if we exchange these indices. If I exchange the indices 1 and 2, then we can see that this expression is identical. It's the exact same, and so we can see that M21 is equal to M12 by symmetry, just by looking at it, because we can see that the integral doesn't change if I change the order of these two integrals. If I reverse them, it's the same. So this is quite nice. And so we can then see that the mutual inductance between two objects is the same. And so what we like to say then, and so instead of saying, instead of saying phi 1 is equal to I2 M 1, 2, we would say instead that we just have the mutual inductance M21 equals M12, and we can just call it M, the mutual inductance. And so basically what we can say then is that the flux through loop I is equal to the current in loop J times the mutual inductance between them. And there's just one mutual inductance. And so this is then is our final result. And so now we can ask a different question where this is just the mutual inductance, which is relating now current in one loop with flux in a different loop. So we'll say current in loop J with flux in loop I. Okay, so now what we can do is we can continue to look at this situation where we have loop 1 and loop 2, and there's some current flowing in them, I1, and there might be some current flowing here, I2, and then we can ask the question, what happens to loop 2 if the current is changed in loop 1? So let's do this. So let's change current in loop 1, and then what happens to the flux in loop 2? What happens to loop 2? And so that's an easy question to answer, because we know that the flux in loop 2 is equal to the mutual inductance between loop 1 and loop 2 times the current in loop 1. And so if we change I1, then that's going to change. If we change the current in loop 1, then that will change the flux in loop 2. And so we can do that. So we can figure that out by just taking the derivative of both sides, d dt, of both sides. And so we see then we have d phi 2 dt is equal to m di1 dt. We're just taking the derivative of both sides. So we see that by changing the current in loop 1, it's going to create a flux, a change in the flux in loop 2. All right, here, this is phi 2, and this is I1. But then, of course, we know that this is nothing more than the EMF, because we know that the EMF in loop 2, which I'll call, here I'll just call it E sub 2, we know that that's equal to the negative change, the negative rate of change of the time of the flux in loop 2. Because remember what EMF is, where EMF is defined as the integral over a loop of E dot dl. Remember, that's what EMF is. And so that means then that from this expression, I see that I can write what we have here then is the negative EMF of loop 2 is equal to m times di1 dt. And so another way of saying that is what we have then is the EMF in loop 2 is equal to negative m di1 dt. And so this is a very famous expression. It's basically, and so this is sort of like, we can think of the EMF as like voltage. And so this is basically saying that the voltage across an inductor is equal to, that if I have a change, if I have two loops, this is loop 1, this is loop 2, and if I'm changing the current in loop 1, then that's going to create an EMF in loop 2. So changing one loop is going to affect the other loop, and the thing that links it is the mutual inductance. So that's how they're linked, and we can think of that a lot like capacitors. The way capacitors are linked as well. You change voltage on one capacitor, you change the charge on one electrode, then you change the charge on a different electrode. Okay, so now let's also consider the fact that just like capacitance, an object can have self-inductance. So we've been talking about mutual inductance, but now let's remind ourselves that we can have an object can have self-inductance. And self-inductance is just what it says. It's the way to think about it is we write our favorite for magnetism. We write our favorite device, which is an inductor, a solenoid. Let's assume there's some current flowing through it, I. And let's assume that there's, say, n turns. And let's assume that it has some length here. I'll call that L. And so then what we can do is we know that this creates some magnetic field. This current, there's going to be some magnetic field inside B. And so then we can see that that will create some flux. And so we have the flux is equal to L times I. And so this then is the self-inductance. And the idea is that it's just the relationship between flux and current. So the flux in an object, the magnetic flux passing through an object is proportional to the current passing through an object if it's all isolated, and that linear relationship is determined by the inductance of the object, L, the self-inductance. And so we can calculate the self-inductance for this solenoid. Let's calculate L. And this is something that you guys have probably done in other classes, but I'll just remind you, is that what we need to do is calculate, the way to do it is to calculate the flux, B, the flux, let's calculate the flux in the object, and then we'll see that it is proportional to I. And then the constant of proportionality is simply the inductance. So let's calculate phi B. So that's going to be, it's going to be the integral over B times dA for each loop. But if there's n loops, then we have to multiply that by n. And so we know that we have so for a solenoid, the B is constant. For a solenoid, we have a constant B, and so we see that this is then just going to be B times the area, where this is the area of our solenoid, times n. So that will be the magnetic flux, and so then we need to know B. What is B equal to? Well, for a solenoid, we remember the simple formula that you derive using Ampere's law. Remember, if I have a solenoid, then I can do the trick, the Ampere's trick. If this is A, I, and then I have n turns over L, then we know that when we do the integral B dot dl of the Amperian loop, it's equal to Ni, and so then we're going to end up with a magnetic field is equal to mu naught, oops, got a little mu naught there, mu naught N over L times I. That's what you get from that relationship that you guys remember from before. And so we can plug that here. And so we see that we have the magnetic field is equal to mu naught n over L times I, that's the B field, times the area times n from this formula. And so then we see that the magnetic field, the magnetic flux in my solenoid is equal to, it's going to be equal to mu naught n squared times A over L times I. And so then we can see that the flux in my object is proportional to the current. And of course, that means then that the proportionality constant is the inductance. And so the L then, of course, is mu naught n squared A over L. So that then is the self-inductance of the solenoid. Okay, folks, I think that is where we're going to stop. So today's lecture is a little bit on the short side, but I figure last lecture was a little bit on the long side, so it all evens out. So I'll see you next time.